The purpose of this video is to explain that section in your notes that's entitled Examples of Mixed Models. In that section, there are three examples of mixed models: randomized complete block, fully randomized design, and random slopes and intercepts. And this is the only one we're going to look at because I'm pretty sure you're familiar with randomized complete blocks and fully randomized designs. So to do that, what I'm going to use is data simulation, because data simulation is a good idea to get our heads around what's the underlying process that gave rise to the data. And so what I'm going to do is going to be based on chapter 12 of Carey, where he's interested in the relationship between the mass of snakes and their lengths. Now the difference is that whereas he has 56 populations of snakes with 10 individual snakes per population, I'm going to only have 3 populations of snake with 3 individuals of snake in each population. And if I think about how those data are going to be set up, what we can have is data frame that's going to have populations, and then we're going to have individual snakes, and this notation is indicative of nesting. And so what I mean by nesting is that snake 1 in population 1 is a different individual snake than snake 1 in population 3. And the predictor variable is going to be the length of the snake. I have some data on snake lengths. And the thing we're trying to predict, the dependent variable, is going to be the mass of the snake. That's what we're all about. And what we're going to do is we're going to use simple linear regression, but we're going to consider it with random slopes and intercepts, because this is really the concept that I'm trying to get our heads around. So in your notes, you've got a figure that looks like this. And the key here is not to get too hung up on these different icons, but rather think about what's actually going on. Think about the way in which the data would actually be simulated. So let's think about this first one first. What I've got in this first instance is a combined analysis. So how would those data be generated? Well, what I would do is I would generate the data by y is equal to alpha plus bx plus e, where this is going to be the intercept, the slope, the residual. And this is going to be my predictor variable. This is going to be my dependent variable. And so what I would do is I would specify a particular value of alpha. I'd specify a particular value of beta. And then for the residual, I'd have a normal distribution with a mean 0 and some specified standard deviation. And then what I would do is I would draw 9 observations. And I would do that by getting 9 residuals. For those 9 different individual snakes, I would put in the value of x. I get the value of y based on some common value of alpha and beta. So I get, there would be population 1, and there would be population 2, and there would be population 3. And this process is clearly inappropriate biologically. And the reason for that is that what this process assumes is that these different populations of snakes are independent. So in other words, we're assuming we've got 9 independent observations, when in reality we've got 3 observations, each of which are clustered within 3 different populations. So this sort of analysis would violate the assumption of independence, and it would be inappropriate. An alternative is to analyze the 3 populations separately. So again, we're going to have y is equal to alpha plus bx, and we're going to have 9 values of the residual that are coming from a normal distribution with mean 0 and some standard deviation sigma. But what's different here is that when we simulate the data with populations separately, what we're going to do is we're going to have a specified value of alpha 1 and beta 1 here, and alpha 2 and beta 2 for the second population, and alpha 3 and beta 3 for the third population. So what we're assuming is that the data are generated by a process in which, although this is the same in a general sense, we're going to have different values that we're going to have to specify in our simulation process for those 3 separate populations. Now we're going to move on to the really important part, because that's what this video is really about, is this concept of random slopes and intercepts. And this may be a bit new to some of you. So what are we going to do here? What we're going to do here is, and again, try not to get too caught up on the icon. Focus on the process by which the data come about. What we're going to assume is that we're going to have a random distribution of intercepts. And so we've got some random distribution of intercepts that has a mean that I'll identify as alpha, and it has a standard deviation that I'll identify as sigma int. And from that distribution, I will draw 3 values at random: alpha 1, alpha 2, and alpha 3. And then I'm going to have another distribution of slopes, that's normally distributed with mean beta, some estimate of variability that I'm going to refer to as sigma slope, and from that I will draw 3 values of beta: beta 1, beta 2, and beta 3. And just as before, there will be a residual that comes from a normal distribution with mean 0 and some standard deviation sigma. So the way these 3 lines are going to come about is that I'm going to have, this guy is going to be based on alpha 1, beta 1, this one alpha 2 and beta 2, this one on alpha 3 and beta 3. What's really important, however, is whereas in this case, I specified with alpha 3, beta 3, alpha 2, beta 2, alpha 1, beta 1, I specified those. Whereas in this case, I didn't specify particular values of alpha and beta. What I did was, I specified the mean of alpha and beta. I specified some index of the variability of the intercept and the slope. Then I randomly drew particular values of alpha and beta from those distributions and used those to simulate the data. So one of the things that's also in your notes that we're going to spend a fair amount of bit talking about is this concept of fixed versus random effects. I'm just going to clean this up a bit. That. And we can think of, in this case, effects are fixed, slopes and the intercepts are fixed. Whereas in this case, the slopes and the intercepts are obtained from a distribution randomly. So what are some of the differences between fixed and random? Go over that some more in the notes. But one thing is that if we were to repeat this experiment with fixed slopes and intercepts, we get the same slopes and intercepts. Because I'm going to choose what alpha 1 and alpha 2 and beta 2, etc. I'm going to choose those. So if I were to do this over again, I'd probably choose the same values. Whereas down here, if I repeat, I get different slopes. Why would I get different slopes? Because I don't get to choose the slopes. All I do is choose the mean slope value, the mean intercept value, and the variability, and then randomly select intercepts and slopes from those normal distributions. So repeating the experiment would give me a different result. So, what else differs? What we tend to be interested in here is the value of alpha and beta. That tends to be our focus. So we'd specify particular alpha and beta. Whereas down here, our focus tends to be on the variability of alpha and I should call this intercept, the variability of the intercept and the variability of the slope. And the third difference is the only random component is the residual error, whereas in this component you have alpha, beta, and the residual coming from a distribution.